Hey folks, welcome to the channel Science Expanse. Let's discuss some useful information about the impact of nanotechnology. Nanotechnology is the science and engineering of manipulating matter at the atomic and molecular scale to create materials with remarkable new properties. Nanotechnology's history began with a 1959 talk by physicist Richard Feynman, where he imagined manipulating atoms and molecules to make new materials and gadgets. The actual term, nanotechnology, was introduced by Norio Taniguchi in 1974, meaning very precise manufacturing on an incredibly small scale, nanometer. In 1981, Gerd Binnig and Heinrich Rohr invented the scanning tunneling microscope, STM, a tool that let us see individual atoms for the first time. This breakthrough, which won them the Nobel Prize in Physics in 1986, was a huge step forward for nanotechnology, making it possible to work directly with atoms. During the 1980s and 1990s, nanotechnology made big strides, especially with the discovery of fullerenes, also known as buckyballs, in 1985 by Harry Kroto, Richard Smalley, and Robert Curl, earning them the 1996 Nobel Prize in Chemistry. Then, in 1991, Sumio Iijima created carbon nanotubes, further advancing nanotechnology with materials that had amazing strength and could conduct electricity really well. Nanotechnology isn't just a modern invention. It's also found naturally all around us. This shows how nature uses tiny, nanoscale structures and processes in various ways. Here are a few examples. Butterfly wings. The vivid colors of butterfly wings are not just a result of pigmentation but also of nanoscale structures that manipulate light through diffraction and interference, creating brilliant iridescence. Gecko feet. Geckos can climb smooth vertical surfaces and even walk upside down on ceilings because of nanoscale hair-like structures on their feet. These structures increase the surface area in contact with the wall, exploiting van der Waals forces to adhere to surfaces without liquids or surface tension. Spider silk. Spider silk is a natural nanomaterial known for its exceptional strength, flexibility, and elasticity, outperforming many synthetic materials. It's composed of protein molecules arranged in a precise structure at the nanoscale. Lotus leaf. The lotus leaf's self-cleaning effect, known as the lotus effect, is due to nanostructures on its surface that repel water and dirt particles. This property has inspired a range of water-repellent materials. Peacock feathers. Similar to butterfly wings, the vibrant colors of a peacock's feathers are not solely due to pigments but are enhanced by nanoscale structures that reflect light to produce vivid and varying colors. Bone structure. On the nanoscale, bone is a composite material made of organic collagen proteins and inorganic hydroxyapatite crystals. This nanostructured arrangement gives bone its remarkable strength and resilience. These examples highlight the sophistication of natural nanotechnologies, which have inspired numerous scientific advancements by mimicking nature's nanoscale engineering. Medieval church windows and certain mollusks provide fascinating examples of natural and early human-made nanotechnology, respectively. Medieval church windows. The bright colors in medieval church stained glass windows come from tiny particles of gold and silver mixed into the glass. These particles change how light bounces off, creating the beautiful reds and yellows we see. This was an early use of nanotechnology, done by trial and error, long before people really understood how things work on such a small scale. Mollusks and nacre. Mother of pearl, or nacre, is a strong and shiny material found inside some mollusk shells and on pearls. It's made of tiny calcium carbonate plates arranged like bricks, with protein layers in between. This setup makes nacre very tough and gives it a shiny look because of how it bends light. Scientists are looking at nacre to create new materials that are just as strong and shiny, using nature's own nanotech tricks. Carbon nanotubes, CNTs. Carbon nanotubes are cylindrical molecules that consist of rolled-up sheets of single-layer carbon atoms, graphene. They can be single-walled, SWCNTs, or multi-walled, MWCNTs, depending on the number of layers. These tubes are super strong, can carry electricity and heat well, making them useful for things like strengthening materials, making electronic parts, and delivering drugs in the body. Nanoparticles. Nanoparticles are super tiny particles, about a billionth of a meter big, made from different materials like metals, ceramics, or plastics. Because they're so small, they behave differently than larger particles, being more reactive and sometimes changing how they look or act. This makes them useful in many areas, such as delivering medicine directly to where it's needed in the body, making electronics like computer chips and screens, and cleaning up pollution. Quantum dots. Quantum dots are semiconductor particles only a few nanometers in size, so small that their optical and electronic properties differ from those of larger particles due to quantum mechanics. They are known for their bright, vibrant colors when illuminated by light, a property utilized in display technologies and biological imaging. The color they emit depends on the size of the dot, allowing for precise control over the emitted spectrum of light. This makes quantum dots valuable in applications ranging from high-resolution displays and LED lighting to medical imaging and solar cells, where they can be used to convert sunlight into electricity more efficiently than traditional solar cell materials. Nanotechnology, with its ability to manipulate matter at the atomic and molecular level, has opened up innovative applications across diverse fields. Here are some novel applications that highlight the breadth of nanotechnology's impact. Drug delivery systems. Nanotechnology has revolutionized the way drugs are delivered within the body, enabling targeted drug delivery to specific cells or tissues, thus minimizing side effects and increasing the effectiveness of treatments. This is particularly impactful in cancer therapy, where nanoparticles can be designed to target tumor cells directly, delivering chemotherapy agents in a more localized and controlled manner. Self-healing materials. Inspired by biological systems, nanotechnology has led to the development of materials that can self-repair after damage. These materials contain nanoparticles or nanocapsules filled with a healing agent that is released when cracks form. This technology has potential applications in aerospace, automotive, and construction materials, extending the lifespan and safety of structures and vehicles. Water purification. Nanotechnology offers solutions to water scarcity and pollution through the development of nanofilters and catalytic nanoparticles that can remove contaminants, viruses, and bacteria from water more efficiently than traditional methods. Nanoparticles can break down pollutants into less harmful substances, offering a promising approach to ensuring clean drinking water worldwide. Flexible electronics. The field of flexible electronics has benefited from nanotechnology through the development of conductive nanomaterials like graphene and carbon nanotubes. These materials can be used to create flexible, lightweight, and durable electronic devices, including wearable technology, foldable smartphones, and electronic textiles that can monitor health indicators. Energy storage and conversion. Nanotechnology has significantly impacted energy technologies, particularly in improving the efficiency of solar cells and developing more effective energy storage systems like batteries and supercapacitors. Nanoscale modifications in materials can enhance the absorption of sunlight in solar panels and increase the storage capacity and charge-discharge speed in batteries, making renewable energy more viable and efficient. Quantum computing. At the forefront of computing, nanotechnology plays a crucial role in the development of quantum computers. Quantum dots and other nanoscale materials are essential in creating qubits, the basic units of quantum information, which promise to surpass the capabilities of classical computers in certain tasks, including cryptography and complex simulations. These applications demonstrate nanotechnology's vast potential to solve complex challenges and improve technologies across healthcare, environmental management, energy, electronics, and computing, paving the way for future innovations that could transform our world. We hope in future we can imagine a world where healing happens at the cellular level. This is the promise of nanotechnology in biotechnology. The nanoparticles, smaller than a wavelength of light, will become the building blocks for revolutionary medical treatments. Doctors can now target diseases like cancer more precisely, reducing damage to healthy cells and minimizing side effects. These tiny warriors can navigate our bloodstream, delivering medication exactly where it's needed, revolutionizing drug delivery systems. Beyond treatment, nanotechnology offers hope in early disease detection, making preventive measures more effective and saving lives. Research in nanobiotechnology is also paving the way for tissue regeneration, potentially healing injuries and diseases previously deemed incurable. The fusion of nanotechnology and biotechnology is not just the future. It's here, promising a healthier world for generations to come. Thanks for watching. Please like, share and comment.